Am I audible now? Yeah, so what I was telling was I will be uh, doing, so for this week, I'll be doing the session on week 3 contents. And on Friday, 6 p.m. to 8 p.m., there will be a session, and that is on the week 4 contents, this week's content, linear regression and all. Because I couldn't do the last week's session. So it's like today we'll be discussing week 3 content, and on Friday, 6 p.m. to 8 p.m., we'll be discussing week 4. Yeah, so in week uh, 4, mainly, sorry, week 3, it is mainly about an introduction to optimization. So the session, it starts with machine representation of numbers. So when we do max on paper, we know that we can write as many decimal digits as we need. But when it comes to computers, we can only store a certain number of digits. So this is called as a finite precision arithmetic or machine arithmetic. Uh, And in the video, Sir also talks about the consequences of such simple representation of numbers, the Ariane 5 rocket explosion. So, as he mentions in the video, the first test flight of this rocket, it was uh, like it got self-destructed 37 seconds after the launch. So, uh, and the issue was that there was a 64-bit floating point number, and it was converted to a 16-bit signed integer. So, that when that conversion has happened and when the rocket has started, there was an overflow error. So there was an incorrect orientation, which resulted in an incorrect orientation, and the rocket has turned 90 degree, and there was a self-destruct that got triggered. So this kind of it is a simple thing that resulted in such a big consequence. So this example was told because when we do things in computer, we should always we should keep in mind that uh, such overflow or underflow can occur. So especially when we deal with a large number or large amount of data, all these things matter. And we work on machine learning model, which are designed to build on a large amount of data. And this large amount of data is represented using some numbers. And this representation of each of this number, it matters a lot. So you will come across when you do data analysis. I hope many of you are from computer science background. So many of you, when you do programming, you come across values like NaN, not applicable number, or infinity. So these are all some errors which shows that the computer cannot represent that number because of some issue with because of some limitation. So we come across this issue when we deal with numbers or any other data type in computer. So one such example was this, like the consequences of it can be huge, and one such example was discussed in the video. So all numbers, if we take the numbers in compute, it can be either integers or it can be decimal numbers. So all these numbers, they are represented as zeros and ones in computer. And there are different types of representation. So, for example, integers can be represented using a 16-bit representation. So, this zeros and ones, these are the bits. And if it is a computer that can support a 16-bit representation, then uh, so in general there will be one bit that is assigned for sign to indicate whether it is a positive number or it is a negative number, and then the remaining 15 bits will be assigned to represent the magnitude. So this means that we can represent 2 raised to 15 minus 1. So you can represent the maximum positive integer that we can represent when we have a 16-bit representation is 2 raised to 15 minus 1. Similarly, for a 32-bit representation, we'll allocate 1 bit for sign, and then the remaining 2 raised to 31 minus 1 numbers we can represent in a 32-bit representation. Now this is for integers. Now when it comes to uh, floating point representation, so again there is a general form for this floating point representation, which is given by plus or minus 1 plus f into 2 raised to e, where f is called as the mantissa, which is the fractional part, and e is the exponent. So this is the standard IEEE standard. Now, in this also, there is something called as a 64-bit double precision. So when it is 64-bit, it is double precision. When it is 32-bit, it is single precision. So for 64-bit double precision, the representation is you will have 1 bit for sign, and then you will have 11 bits for the exponent part, and you will have 52 bits for the mantissa part. So then in the video, sir talks about what is the maximum number you can represent with this representation and what is the minimum number. All these things are discussed. So you can refer to that to understand what is the maximum and what is the minimum number. Now then coming to overflow, underflow. So overflow occur when a number exceeds the maximum representable value. The computer will either return infinity or it will return not a number kind of error. And underflow is when the number is too small to be represented. So then the number might get rounded to 0, and this can cause division error. So then there is something called as a condition number. So in condition number, this is in cases. So suppose if I have a system of equation which are represented in the format ax is equal to b. So we say that this system or this matrix is ill conditioned. The matrix is A here. So the matrix is ill conditioned if for any small change in the input, if it causes a big change in the output. So if there is a small change in B, if it causes a drastic change in X, then we say that the matrix is ill-conditioned. So this is something that is important when we come to for example, the analytical solution of a linear regression. I don't know if that video is already covered. So, in analytical solution of analytical solution for linear regression, you have to you have an equation in this format ax is equal to b, and then you have to find what is x. So you get a representation here which will involve the pseudo inverse of a times the b. So this part, if the matrix is an ill-conditioned matrix, then it will affect this part. So, so that is also one thing that is, I mean, this condition number is an important factor when we deal with such solution or analytical solution. Now, another, so in the second part of the video, uh, I mean, in the second video, so starts with discussing about derivative, gradient, Hessian, Jacobian, and Taylor series. So when we talk about derivative, so the derivative is something that, so it's a measure. So it measures how much a function changes when the input changes slightly. So it is mainly if you take it is the slope of the uh, it is a slope of the tangent line at a point x. So that is derivative. I hope that is already something that we have been studying for a long time. And then coming to partial derivative. So when a function has multiple inputs, so suppose there is a function f, and if it has multiple inputs, say x1, x2, etc., up to xn, how much? So the question is, partial derivative answers this part, like how much does f change if we change only one variable while keeping the others fixed. So that is what a partial derivative is. So it's denoted by dou f by dou x1, dou f by dou x2, etc. And then gradient. So gradient is a vector of all the partial derivative. So it tells you the direction of steepest increase of the function. So there will be so the gradient always points in the direction of maximum increase, and a negative gradient points in the direction of steepest decrease. So that is a gradient. And then Hessian matrix is the second order partial, is a matrix of second order partial derivative. So, and then Jacobian is a gradient that is generalized to vector valued function. Then, so I will give some example questions on this. Then Taylor series, it approximates a function near a point using its derivative. Uh, and it is something that we have been studying for a long time with respect to calculus or physics. And now we are going to deal with it in machine learning. So I will give two example question. Yeah, sorry, I was writing the question. Okay, so I have given five practice questions. Can you try this and let me know? I'll give 5 to 10 minutes for this. Yeah, so I hope everybody knows most of these things. So just for those who don't know, I think it would be good if you go and practice some of the gradient essay and all those questions, because when we come to neural networks, or when we come to many machine learning models, we have to do some gradient calculation. For example, in backpropagation, you have to find partial derivative and all those. So it's better that you practice many questions in addition to whatever we discuss. So the question is, find the gradient of f of x comma y. So f is a function of two variables x comma y, and you have to this function is given, and what is the gradient at the point 1 comma 1. So how do we do this? We take the partial derivative, because it's a function of two variables x and y. So dou f by dou x is given by uh, so 3x square 6x, and 2xy has 2y. Now they have also asked what is the gradient at the point 1 comma 1. So you substitute for x 1 and substitute for y 1. So then you get 6 plus 2, which is 8. Then dou f by dou y. So that first term is 0. So second term is 2x minus 3y square. And then substituting 1 and 1, we get 2 minus 3, which is minus 1. So the gradient at 1 comma 1 is 8 comma minus 1. Okay. Now the next question is, you have to find the Hessian of f of x comma y. So Hessian is the second derivative. It's a matrix of second derivative. So here we first find what is dou f by dou x. So dou f by dou x is 2x plus 4y. 2x plus 4y. Then dou square f by dou x square, because we have to find the second derivative. That is the derivative of this with respect to x. So that is 2. Then we find dou f by dou y, which is which is 4x plus 6y. So 4x plus 6y. Then dou square f by dou y square is equal to 6. Now, so this dou square f by dou x square and dou square f by dou y square, this forms the diagonal elements of the Hessian matrix. That is 2 and 6. Now we need to find this one and this one. And we know that this is a symmetric matrix. The Hessian matrix is a symmetric matrix. So this value and this value will be same. So we can just take one of them and find the derivative. So here, if I take dou square f by dou x dou y, I'll get 4. So here it is 4. So this is the Hessian. Now the next question is, find the critical point of f of x comma y is equal to x square plus y square minus 4x minus 6y plus 13. So critical point is where the dou f by dou x. So this is the point where dou f by dou x is equal to 0, and also dou f by dou y is equal to 0. So dou f by dou x is 2x minus 4. So this is 2x minus 4 is equal to 0. And this is 2y minus 6 is equal to 0. So this will give x is equal to 2. And this will give y is equal to 3. So the critical point is 2, 3. Now compute dou f by dou x of x of, so f is a function of three variables. We just have to find what is dou f by dou x at 1, 1, 1. So dou f by dou x is equal to 2x yz plus y square z. Then you substitute for 1, 1, 1 for x, y and z. So we get 2 plus 1, 3. Hmm. Find the gradient of f of x1, x2, x3 is equal to x1, x2, x cube at 1, 2, 3. So to find the gradient again we take dou f by dou x1, dou f by dou x2, dou f by dou x3. So dou f by dou x1 is x2 x cube square, and we know it is 1, 2, and 3. So you can substitute for x2 and x3. So that is 2 into 3 square, which is 9. So it is 18. Then dou f by dou x2 is x1 x cube square. So x1 x cube square, and that is equal to 1 into uh, 3 square, that is 1 into 9. Then dou f by dou x cube is 2 times 2 x1 x2 x3. So x1 x2 x3 1 2 3, if we substitute 2 into 1 into 2 into 3. So that is 12. So the gradient is at 1 2 3 is 18, 9, 12. Okay. So okay. Now I have a multiple choice question. So if H is the Hessian at a critical point and all the eigenvalues are negative, then the point is a local minimum or a local maximum or it is a saddle point. So H is the Hessian and if all the eigenvalues are negative, then that means this is a negative definite matrix. And when we have a negative definite matrix, uh, the critical point will be local maximum. And when we have a positive definite matrix, the critical point will be local minimum. If it is semi-definite, that is, it contains zero values, then it is a saddle point. So the answer is B. It is a point of local maximum. So at a local minimum, what is true about the gradient? Whether it is 0 or it is 1 or it has magnitude 2 or it is not equal to 0. Yeah, so it is the gradient will be 0. Yeah, so it will be a saddle point because it's 0. So in which direction the gradient always points? Is it in the direction of steepest descent, or it is along the contour lines, or it is in the direction of steepest ascent? So the gradient always point in the direction of steepest increase of f. So this delta f always points. So it points in the steepest increase of f. So there was that video where sir takes the f times the directional uh, derivative of f with, along the vector v, and this can be written as the dou f cos theta, and this is maximum when theta is equal to 0. So this is the direction of steepest increase, but this is minimum when theta is 180, that is in the opposite direction, that is steepest decrease. So the negative gradient points to the direction of steepest decrease, and gradient always points in the direction of steepest ascent. So the answer is uh, option D. So function f of x comma y has a gradient 0 at point a comma b. The Hessian is 3, 0, 0 minus 2. What is a comma b? Yeah, so uh, so the Hessian will tell us if it is minimum or maximum or it is a saddle point. And when we take this Hessian, it is a diagonal matrix. Sorry. So only the diagonal elements have non-zero values. So the eigenvalues 4, this 3, 0, 0 minus 2. The eigenvalues are the diagonal elements. So the eigenvalues will be 3 and minus 2. And you can see here that it's neither. So if all the eigenvalues lambda 1, lambda 2, if both of them are positive, then we say it is a local minimum. If both of them are negative, then we say it's a local maximum. But here you see one is positive, one is negative. So it is a mixed sign. So in this case, it is a saddle point. It is not positive not positive definite or negative definite. So in that case, it is a saddle point. So the answer is C. Yeah, so you have to find the Hessian here. The double derivative. So you have to take the double derivative. So x square y plus y cube, the double derivative. The first derivative will give 2xy. And when we take derivative again, it is 2y. And dou square f by dou y square. So when we take the first derivative, we get x square plus 3y square. And when I take dou square f by dou y square on x square plus 3y square, I get 6y. Then dou f by dou x is 2xy. So dou square f by dou y dou x is equal to 2x. So the answer is A. Now, in the lecture, there are there's a video on advanced calculus where some formulas or some derivations on uh, uh, some like matrix vector combinations are shown. So, one question that is based on this is the question is, For symmetric A, what is the derivative of x transpose AX? Yeah, so this is again for you to know. So yeah, now coming to the topic of optimization. So optimization finds the parameter x star that minimize or maximize an objective function f of x. So it will find this value x star that minimize or maximize f of x. So this f of x, the objective function, we also call it as a cost function or a loss function, the function that we want to minimize or we want to maximize. So there are two types. One is unconstrained optimization, where we don't have any restrictions on the value of x. But if we have some restrictions on the value of x, then we go for then there is constraint optimization. So again, the critical point is something that we have discussed, where the gradient is 0 in case of unconstrained case. And in case of constrained optimization, we minimize this function f of x subject to certain constraint. And this constraints, so this is subjected to some constraint, and this constraints can be either equality constraints or it can be inequality constraints. So equality constraints is where, for example, g of x is equal to 0 and inequality is h of x less than 0. That is one inequality. That's right. So to solve this, one way to solve this is to use the method of Lagrangian multipliers. So if we want to minimize or maximize f of x subject to the equality constraint g of x and inequality constraint h of x, then we write this as L of x comma lambda comma alpha is equal to f of x, the function that we want to minimize or maximize, plus lambda times the equality constraint plus, I'll remove the this sign for now. Just I'm not using the summation for simplification. So then alpha times h of x, the inequality constraint. So this is the Lagrangian, generalized Lagrangian form. And here the lambda is the Lagrangian multiplier for equality constraint and alpha is the Lagrangian multiplier for inequality constraint. Okay. Now, then in the next video, sir talks about gradient descent. So in practice, we often cannot solve the gradient is equal to 0 analytically. So gradient descent is an iterative numerical method. So it is an iterative numerical method to find the minimum. So you have a function f and you want to find the minimum for that. And the one way to solve this iteratively is to use gradient descent algorithm. And there is a gradient descent update rule. And this is so there are certain parameters, and one such parameter is this W. So what this W is, we'll study in the coming classes. So there is a function J, and this J is expressed in terms of certain parameters, and one such parameter is this W. So W of k plus 1 is W of k minus alpha times the gradient of J at W of k. So this is the gradient descent update rule. So for the k is the iteration. So this is iteration k, and the value of W at the next iteration is given by the value of W at iteration k minus alpha, which is the learning rate, or it is also called as the step size, and the gradient of the cost function or the objective function. So this tells you to move towards the direction of steepest decrease. That is y minus delta j. Now there is this parameter called learning rate. So in the videos talks about different substituting for different values of learning rate, and then talking about their consequences. So one thing is, when alpha, or the learning rate, when it is too large, then the algorithm diverges. It oscillates wildly. And when alpha is 1, then again uh, it oscillates a lot. And when alpha is small, so in the video it's 0.1, it takes many iterations. So then when alpha is small, it is 0.1, it takes many iterations, but it converges slowly. Now when alpha is, as shown in that video, when alpha is 0.5, the algorithm converges quickly. So, but in general, this is not a fixed rule. Like, it's not a general rule that if you use alpha is zero point 0.5, then always your algorithm will converge quickly. It's not the case. It depends a lot on your data and your model, many things. So, this alpha is something that we can, play with, or you can. So here comes this hyperparameter definition. So you don't know the value of alpha. So what you do is you takes a range of values for alpha. So for example, you take values 0.001, 0.01, 0.1, or 0.0001. You take a range of value, and then you find uh, for what value of alpha your algorithm kind of uh, uh, gives a good optimum. So, for example, by optimum, what we mean is it could be anything. So, for my case, I want to reduce the error. So, I predict. So, I have a model M, and it's a classification problem. So, I want to classify between cat and dog. So it's a, let's say it's a binary classification, 1 and 0. Or let's say, it's a regression problem where I predict stock prices. So what I want to do for my model in this case is I have a prediction and the model already has, there is a ground truth value also which I denote by x cap. What I want is to reduce the difference between my prediction and the ground truth, the actual value or the actual label. So this error I want to reduce. So this is my objective. And if I plot the error versus the alpha for different learning rates, then if I see that for a certain value of alpha, my algorithm converges and also the error is like kind of the smallest and also it is stabilized, like it's not changing after a certain number of iterations, then I can say that that is the best learning rate. So this is something called as hyperparameter tuning, where we have certain parameters that we don't know, like what is the optimum value for that parameter. So what we do is we search for what is the optimum value of alpha, such that certain condition must be satisfied. So for in this case, I want to minimize my error, but I don't know what is a good value of alpha. So for that, I try for different values of alpha, and then finally I get a good value of alpha that is good for the data or the problem that I'm dealing with. So alpha is basically a hyperparameter, and it is some. So then the last topic was stopping criteria. So so either the stopping criteria could be that the norm of the parameter is less than a very small value epsilon, or you can take the gradient magnitude and say that is less than epsilon, or we can take the difference, the cost change, and say that is less than epsilon, or you can also say the number of iterations. So we train for a certain number of iterations. After that, we stop. So that could be a stopping criteria, because we cannot keep on doing this gradient update again and again. So we stop at a certain point. And for this, there are different stopping criteria, and that is what all these are. Okay. Now we solve some questions. Yeah, so f of x is equal to 4, f dash of x is 4x cubed minus 8x. So this, we can take x as common. So 4 is also common. So 4x times x square minus 2 is equal to 0. And you get x is equal to 0 and x square minus 2 is equal to 0 means x is equal to plus or minus root 2. So there are three critical points. So in gradient descent, what is the learning rate alpha? Yes, it is a hyperparameter that controls the step size in each iteration. Okay, so the cost function j is w1 square plus w2 square plus 4, and the initial value is 3 comma 4 for w1 comma w2, and the learning rate is 0.5. So what is the new value of w1 w2 after one iteration, that is after one update? So the update is w new is w old minus alpha time the gradient of j. So the gradient will be 2W1 and then 2W2. When we substitute for W1, W2, it is 3 and 4. So 2 into 3, 6. 2 into 4, 8. Now alpha is 0.5 and W old is 3, 4. So alpha times the gradient is 3, 4 because 0.5 into 6 is 3, 0.5 into 8 is 4. So W new is 3, 4 minus 3, 4, 0, 0. So when the learning rate is too large, what can happen? Whether the algorithm will converge slow, fast, or diverge. Yeah, so the algorithm will diverge. So after one iteration of gradient descent on J, W1 square plus W2 square plus 4, uh, starting at 3, 4, what is the new W? So the gradient is 2W1, 2W1, 2W2. So W1, W2 is 3, 4, 6, 8. So alpha is 2. So alpha times delta W is 10. W new is equal to W old minus alpha times delta J. So that is 3, 4 minus 12, 16 minus 9 minus 12. What about the value of j at this point? Minus 9, comma, minus 12. What is the value of j at this point? What is the value of j at 3, comma, 4? So at kth iteration, the j is 29 and k plus 1 iteration, j is 229. So is the algorithm converging? No, because the cost j has increased. So the algorithm is diverging. So after one iteration, what is W1? So the gradient is 6W1 minus 12, and with respect to W2, it is 4W2 plus 10. So the starting point is 0, 0. So it is minus 12, 10. Now alpha is 0.1. So alpha times is minus 0.1 into 12, 10 into 1.21. Then W1 new is equal to W1 old minus alpha times tau of J at W1. So that is W1 is 0 minus 0.1 into minus 12, that is 1.2. So this is minus. So the W1 is 1.2. So what does it mean for gradient descent to converge? Is it the learning rate reaching 0, or is it the gradient becoming very large? Is it the cost function, or the parameters stop changing significantly, or is it the algorithm? So what does it mean for gradient descent to converge? Is it the gradient becoming large, or cost function or parameters stop changing, or algorithm finding the local maximum? Yeah, so the cost function or the parameters stop changing significantly. Yeah, you can ask. What was the doubt? I cannot hear you. I cannot hear you. So maybe, yeah, there is some noise only. Maybe can you write the question in the chat? Meanwhile, I write the next question. So which scenario would gradient descent reach the global minimum with certainty? Non-convex function with multiple local minima. Convex function with a unique global minimum function with a saddle point near starting point. Which scenario would gradient descent reach the global minimum with certainty? Non-convex function with multiple local minima, convex with a unique global minimum, function with a saddle point near starting point, function with discontinuous derivative. Yeah, so for the question, if the cos function is stabilized, so if cos function is stabilized, then for a certain number of iteration, the cos function will not change. So at kth iteration, the cos function will be j. For k plus 1 iteration, the cos function will be j. For k plus 2 iteration, the cos function will be j. So if it is not changing, we will say that uh, it's not changing anymore, or it is not getting minimized anymore. So that in that case, we will say that the convergence has reached. So that is one of the, so we have those four criteria for stopping the iterations, right? So we cannot indefinitely keep on updating the weights or the parameters in the algorithm. So at some point we have to stop. So one such criteria is that norm of the change in the cost function at a certain this if this change if it is zero, or if it is a very small number that is close to zero, then we will stop. It may or may not mean convergence. So convergence can be like it can either lead to a local minimum or it can lead to a global minimum. So we'll stop at that point when we don't see like when we don't see a change in the cost function, in the different iteration, kth iteration, k plus 1th iteration, k plus 2th iteration, etc. So that if we don't see any change, we just stop there and we assume that the algorithm or the weights have converged to a local minimum or a global minimum. So that is one of the stopping criteria. So here they're asking with certainty, when can we tell that the gradient descent has reached the global minimum? So as shows in the video, there can be local minimum or there can be global minimum, the minimum of all the possible values. So when can we say for sure that the global minimum has reached this? When we have a gradient descent can result in local minimum or global minimum. Um, so it depends on a various number of factors. And when we have a convex function, so a function like this, so for example, we have the error, so x minus x bar, the whole square. So this is a convex function. And here we know that if you find this is the local minimum as well as the global minimum. So in this case, we can tell for sure that gradient descent has reached the global minimum with certainty. So this is an example of a convex function with a unique global minimum, but not in the other cases. Given J is 3w square minus 12w plus 15, what is the minimum and where does it occur? So when we take the derivative dj by dw, we get 6w minus 12. We take second derivative is 6 and 6 is positive value. So this is minimum. So then the minimum is 3 from the option. It is minimum 3 at W is equal to 2. So 12 plus 15 minus 12 into 2. So 24. So it is minimum occurring at W is equal to 2. Yeah, so when we take the derivative, we get, so from previous thing, we know it is 6, 8. And W new is W old minus alpha times 6, 8. So we get 3 minus 3 minus 4. So then again we find the next, that will be minus 6 minus 8 at minus 3 minus 4. And when we substitute, we get W new is minus 3 minus 4 minus 1 times minus 6 minus 8. So we get 3, 4. So it will oscillate between 3, 4 and minus 3 minus 4. In 16-bit signed integer representation, what is the maximum positive integer? In 16-bit bit signed integer, what is the maximum value. Yeah, so it is 32767 because it is 2 raised to 15 minus 1, 1 which is assigned for sign. So in IEEE standard for double precision, which is 64-bit, how are the bits allocated? So in IEEE standard, what is the bit allocation? Yeah, so it is 1 sine, 11 exponent, and 52 mandisa. So what will cause an overflow error? So overflow occur when the number exceeds the maximum representable value. That is, the number will, so there will be error when there is overflow, like it will return either NaN or infinity. Uh, so in which of the following 4 cases an overflow will occur? And in 16-bit, 64-bit, there's double precision. The maximum number that can be represented is around 1.8 into 10 raised to 308. So, when we consider this, this is very greater than this number. So, this case will throw a overflow error. So as in normalized floating point representation, how is the binary 5.5 represented? So 5 in binary is 101. 0.5 is 0.1. So 101.1 is 5.5. So then, but in normalized form for binary, we represent it as 1.011 because we shift 2 decimal places left. So 1.011 into 2 raised to 2. So for f of x is e raised to x, the Taylor series around x0 is equal to 0 to second order. So this will be f of x and around x0 is equal to 0, f of 0 plus f dash of 0 into x minus x0, and x0 is 0. So it is 0, so x. So it is x plus f double. So 1 by 2 factorial into f double dash of 0 into x square. Up to second order is what is mentioned. So into x square. And f of 0 is e raised to 0, and that is 1. F dash of 0 is again f dash of x is e raised to x itself. So it is also 1 into x. So it is x and then 1 by 2 into f double dash of 0 is also f, it's 1. So x square. So it is 1 plus x square by 2. So it is 2 raised to 2 because it's in binary format. So base 2, when you shift decimal places, just like in decimal, like when we have 10, when we shift decimal places, we multiply by 10 raised to something. No, it's like that only. So that's why we multiply it by 2 raised to 2. So you shifted 2 decimal places to the left. So that's why it's 2 raised to 2. So if you shift a decimal number 2 places to the left, you get 10 raised to 2. Just like that. It's 2 raised to 2. Yeah. So on Friday, so I will be discussing this week's content, and the time is from 6 p.m. to 8 p.m. on Friday. So if you are free, you can attend the session. So I'll be discussing this week's content on Friday, 6 p.m. to 8 p.m. Yeah. Thank you all for attending.